Okay, let's talk about the Java toolchain very briefly, and we'll get into a lot more detail in class. Let's start by comparing the C++ toolchain. So I mentioned this briefly in an earlier video, and I actually left a few steps out in that earlier description. But basically, when we write code in C++, we edit source code. So we write code in our .cpp files, and then the bit I left out was the fact that we also have these header files, these .h files, that we define classes and constants in. And then before we actually compile the .cpps, the first step before compilation is we send our code through this thing called the preprocessor. And this tool handles any line that starts with a pound. So the pound includes and if not defines and pound defines, things like that. Okay. Once all that code is run through the preprocessor, it is sent to the compiler, and the compiler compiles the source code. So the .cpps might have some stuff injected in them from the preprocessor. So the compiler only looks at these .cpp files, and the compiler generates an object file, one for each CPP. And then there's another tool called a linker, which we send all the objects files through the linker, and then the linker spits out the executable. So I kind of summarized it before is by saying we have these .cpp files, and they get sent to the compiler, and the compiler spits out an executable. And that's the short version. The somewhat longer version has the preprocessor and the linker. Now, the toolchain in Java is a little bit different. We do start by editing source code, okay, and then we compile our source code into bytecode. Okay, we load or invoke the JVM and tell the JVM which.class files to execute. Then there's this bytecode verification stage. And then lastly, the JVM will interpret the bytecode and turn it into real machine instructions. Okay, so I thought I'd go through this once really quickly, and we'll see this again. Okay, so I'm going to, just working from my command line here, list the contents of this directory. Right now it's empty. So I'm going to write a source code file. I'm going to use probably the worst editor I can think of. So this is Pico. This is going to create a file called helloworld.java. So I think I mentioned all source code files in Java end with this .java extension. Okay, so here's my editor. Let's say public class hello world. Don't worry too much about the details here. We'll cover all these in a later lecture. Okay, now I'm going to say system.out.println. It's basically our equivalent to cout. Okay, now I'm going to save this and leave the editor. So now if I list the contents of my directory, I have one file called helloworld.java. The next step is to compile the source code into bytecode. So in Java there is no preprocessor, and if we want to invoke the compiler, we use this command javac for Java compiler, and we give the name of the file or files that we want to compile. So I'm going to say javac helloworld.java. And I'm going to list the contents of this directory again. Now notice there are two files. There's helloworld.java and helloworld.class. And the helloworld.class, that's the bytecode. That has the compiled helloworld.java into these virtual machine instructions. Okay, so you might be wondering, well, why not just interpret the source code? There are plenty of interpreted languages out there that actually do that. At runtime, it'll look at the source code and turn that into something executable. So languages like Perl and Ruby and Python, those are all interpreted languages that actually interpret source code. The reason Java chose to be both a compiled and interpreted language, remember the JVM interprets the bytecode, but the reason we compile the source code first is that the compiler can check for syntax errors. So remember, Java is a strongly typed language. We kind of define the rules of what these classes are and how they should be used, and we can have the compiler verify that we're using them correctly. Another reason why we compile source code is that bytecode is much more compact than source code. It travels much more efficiently over the network than source code would, with all the comments and just raw source code files. So bytecode, it cleans up a little better, it compacts nicely, and it makes it easy to send it over the network. Okay, the next step would be to load the JVM and tell the JVM which .class files to execute. Okay, so all source code files, hello world.java, for example, is turned into hello world.class. So all bytecode files end with this .class extension. And the way we do that, the way we invoke the JVM is we say Java, and we specify the name of the file that has a main function in it. So you might have noticed I wrote a main function in hello world. Okay, so if I do this, you'll see that really two things happened here. When I said Java hello world, the Java command invoked the JVM. Okay, the JVM is a program just like any other. And we told the JVM to go start executing these instructions in hello world.class. And when it did that, the only thing that happens in this program is it prints out hello world. Okay, now there's there was a step in between there. So loading means starting the JVM, and then step 5 was to actually interpret the bytecode and turn it into real machine instructions. The step in between is called bytecode verification. So any .class file that comes from the internet is checked to make sure that it can't damage the machine. This is that whole idea of sandboxing that I mentioned earlier. So if you are downloading your bytecode from the internet, you can still have that program write to the file system if the author digitally signs the code. And to be digitally signed just means that we are definitely verifying the author of the code is who they say they are. So if Google, for example, wants to distribute some code, they can digitally sign it, and we will be guaranteed that that code is actually coming from Google. Okay, and then the last step, like I said, was when the JVM interprets the bytecode and turns it into machine instructions that the real machine executes, that my machine is executing. And of course, this is a little bit slower than compiled C++ code because it has to go through that interpretation step. But this is really only noticeable in the most demanding environments. There are also these things called just-in-time JVMs that store the interpreted results of interpreted code. So think of a while loop, for example, that's going to iterate 1,000 times. Well, really, a just-in-time JVM only needs to interpret that bytecode the first iteration of the loop, and the other 999 times, the JVM will just use the cached or the stored interpreted loop body for later. And this makes things actually run pretty well. Nowadays, you can't really tell whether a program is being run by JVM or in the raw C++ code running at the machine level. Because again, our hardware is so good these days that it's not really an issue anymore.